Hello and welcome to Alkenes 6. So there's no new content in this lesson. It's very much an opportunity to kind of review and consolidate a couple of bits and bobs, including a little bit of revision from before the alkenes topic and just general organic chemistry. It's not going to be super long. It's mainly tasks. There will be some explanation, but it's mainly sort of things to work through on whiteboards or on paper as appropriate. So let's make a start. You should absolutely do this bit without your notes and see how much stuff you can remember. Because if you're not doing that regularly, then you're not going to get a genuine idea or a genuine sense of how much stuff you've actually got memorized. And that is an important part of learning any subject, whether people like it or not. So you should attempt this next set of questions without your notes. All right, let's have a look. So here we are, some starter questions, mainly alkenes, but just a little bit of generic nomenclature and isomerism as well. Okay, so pause the video and attempt to answer these. We'll look at the answers very quickly. Okay, so you should have had a go at all these questions, all right? I'm not going to read through these, right? I'm just going to show you. There's your definition. There's your geometric isomer. Molecular formula, displayed formula. Mechanism question. That would be electrophilic addition. In case I put name, I can't remember if I did or not. Okay, so then that's a quick task, right? I don't know how long it would have taken you. It doesn't really matter, but it's a starting point. The next thing to do is to have a look at some slightly trickier questions. So in this next section, I am anticipating that you'll have a go at the questions, but they are a bit on the sort of slightly harder side. And so if you're struggling and you want to wait for the explanation, that's okay, I understand. But you will still get something from having a go initially. So let's have a look. There are 4 to look at, okay? So this one, it's really the wording and the way the question's formatted that makes it a little trickier. Have a read of it and see what you think. Okay, so this is something that was taken from an exam question. This often happens, not just in this topic, but a lot of the time, exam questions that make you work in reverse can be difficult. And in this case, what we've got is the information about a product, right? So this product is formed by a reaction of an alkene with bromine. So in order to work this out, we're going to have to basically go in reverse, right? So let's draw 1,2-dibromo-3-methylbutane. Again, if you weren't sure where to start, but now that I've said that, you think that's a good idea, why not pause the video and have a go? It's up to you, right? So we've got 4 carbon atoms because we've got bute. We also have a methyl group in position 3, and then bromine atoms in position 2 and 1. Okay, so we don't actually need to fully draw out the DF, but what we'll probably do is make sure that we know where there are hydrogen atoms. So that is 1,2-dibromo-3-methylbutane, right? And actually, now that we've drawn it, it probably doesn't look that scary, right? If you think about it this way, this is the end point of an equation, essentially, right? There's no consideration of minor or major product here, right? Because bromine, as an electrophile, regardless of which order the bromine atoms get added across the double bond, and it will happen in a particular order, but that doesn't really matter because we're not drawing the mechanism, and the outcome is that you end up with a bromine in position 1 and a bromine in position 2 anyway. The main thing to realize is that actually this section of the molecule is completely the same, so we can transpose, which is a fancy word for copy, that section of the structure. Okay, and there it is. And then where the bromine atoms have been added, that must be where the double bond was, because it's an addition reaction, and we know that we formed this molecule from an alkene. So that means we have a double bond between those 2 carbons, right? We're going to have the requisite number of hydrogen atoms. which is that many. Okay. A quick sense check shows us that all the carbon atoms have 4 covalent bonds. All right. And that is our answer. So again, it looks a bit scary, mainly because it gives you the answer and asks you to work backwards. And this happens a lot in redox as well, actually, where the phrasing of a question can sometimes cause bother, but it's not actually that difficult. Okay, let's keep going. Again, a question that's often underestimated is this type of question, right? Might as well introduce this. We haven't done many of these yet, right? But we have done this one. So you can read it and have a go. You might not be sure what to put for each section, but you can have a go at least. Okay, so I'm assuming that you've at least tried to recall the reagent and the observation with ethene, okay? So what we should be saying is that our reagent is bromine water. That's the name we give to it, right? Bromine dissolved in water. And the thing that you're supposed to know about this is that in the presence of an alkene, an orange solution turns colorless. It turns into a colorless solution. We sometimes use the verb decolorize. We sometimes say it decolorizes. The orange solution decolorizes. We never say clear, as explained in the lesson where we talked about the bromine water test, because that's not really a helpful statement. Okay, orange solution to colorless solution is the observation with ethene. And remember that that's your kind of positive result. It proves that ethene has a carbon-carbon double bond. We know it does, but what we're saying is it's not just ethene, it could be any alkene and you would get this result. Ethane is an alkane. And so this might be the bit that where people are not entirely sure what to put. The whole point about this is, right, it will not decolorize. So there are a few different ways you can phrase this. You could say solution remains orange. That's one phrase you could use. Orange solution stays orange or something like that. The phrase we tend to use is one that goes no visible change. Sometimes abbreviated to NVC in mark schemes, but I would always just write it in full. No visible change. What that means is, what we just said, the orange solution would stay orange. You could probably get away with no change or no reaction, depending on the question. But if we're nitpicking, it's not as good a way of kind of phrasing it. And the reason for that is that there might be some underlying chemistry that you can't see, even though there's been no visible change. Now, obviously, with bromine water and ethane, we can assume that there is no reaction. But the idea is that you're kind of covering yourself by saying no visible change. And that is the appropriate language to use in these types of scenarios when you're doing name a test tube reagent that can tell between this thing and that thing. This comes up a lot, not just in organic chemistry, but in inorganic chemistry when testing for group 7 ions and, you know, various other things, carbonate ions or whatever, right? It's a big part of A-level chemistry. Again, this might be one of the first times you've seen a question like this, and it might have been the middle bit that threw you, if anything, okay? Which is what makes it a little trickier at this stage. Let's have a look at the next bit. So recalling a little bit of mass spectrometry, right? This is basically asking you to deduce the structure of an alkene. The only bit of help I'm going to give you here is to remind you that a molecular ion peak is basically the molecule having lost one electron. And so the mass to charge ratio of the molecular ion is effectively the same as the molecular mass in this case. I'll go into a bit more depth when I do the answer, but pause the video and see if you can figure it out. Okay, so I'm pretty sure that I added this, all right? Remember that actually there are two types of mass spectrometry or two types of ionization that you're supposed to know about for A-level chemistry. And in electrospray, the mass to charge ratio is not the same as the MR. In electrospray, you have to subtract 1 from the data to account for the fact that a proton was added to turn the thing into an ion. If that all sounds like gobbledygook to you, go back and look at your notes on mass spec, okay? In electron impact mass spectrometry, as I said earlier, the molecular ion peak is essentially, that number is essentially the same as the the relative molecular mass of the compound. So what we're saying is we're looking for an alkene with an RFM or an MR of 42. So there's an element of trial and error to this, right? You could probably do it mathematically if you wanted to, but given the size of the alkene we're probably dealing with, it's, it really is easy enough to do it in terms of trial and error. So my starting point is going to be, well, if I've got ethene, what's the MR of that, right? Because that's the simplest alkene there is. So each hydrogen contributes 1, so I'm looking at that end, 2, 2, 12, 12. So we've got 24 plus 4, so we're dealing with something with a RFM of 28. Okay, so that's clearly not correct. That's not our answer. It's not big enough. So let's add a carbon atom, see how that looks. Clearly this is going to be propene. Okay, so 2 from hydrogen, 1 from hydrogen, 3 from hydrogen, 12, 12, 12 for each carbon atom. So that top line there, that's 36, okay? Then 2 plus 1 is 3, plus another 3 is 6. 36 plus 6 gives us 42. Bish, bash, bosh. The alkene is propene, okay? Now, obviously, this only really works on any kind of reasonable timescale if the alkene's nice and small. If they start doing stuff like giving you an MZ of 100 and whatever, there would be too much trial and error, and they don't do that anyway. What they would do is probably give you some more information, right? I don't know what they'd give you, but they'd give you some additional info, right? To give you some kind of pointer towards the general size of the molecule. So that's the answer. It's propene, but since we're talking about mass spectrometry, now we've figured out that's the RFM of propene, it's worth pointing out, right? C3H6 is the molecular formula of propene. The thing that we're actually looking at, remember, is that as a positive ion. So it's still got 3 carbons, it's still got 6 hydrogens, but it has lost an electron by electron impact ionization. And so the signal that you see in a mass spectrum at MZ42, okay, is due to this. It's not just due to propene, it's due to the molecular ion formed by electron impact ionization of propene. Again, while we're talking about this, if you were to do electrospray ionization on propene, which you wouldn't because it's a nice small molecule, but let's just say for the sake of argument, right? Normally electrospray is used for much larger substances, usually proteins and polypeptides and stuff like that. But let's say you did, then your propene molecule would not have lost an electron. It would have picked up a proton from the solvent that's used in electrospray ionization. And so the ion that would cause the signal would look like that, right? Or I suppose you could write it like this if you wanted to make it totally clear that that proton had been kind of stuck to it, which means that the signal would be seen at 43. But that would only be relevant if it was electrospray. And like I said, electrospray typically is used for much larger molecules because it stops them from breaking up in the mass spectrometer, basically. All right? You wouldn't normally do electrospray on a small hydrocarbon like propene. Right then, let's keep going. Again, I'll just point out, if you really found that difficult to get your head around because you haven't looked at mass spec for a while, now's a good opportunity to go back and have a quick review and then maybe have another go at a question, right? Here's my last one. Okay, again, this is pinched from an exam question. I've kind of, rejigged it a little bit, but it's basically pinched from an exam question. So what I've done is I've set up a little scheme of reactions, right? There are 3 conversions, so there's quite a lot to look at. Okay, this is one of the first times maybe that you've seen like a synthetic roadmap. So in organic chemistry, a lot of the time there are a huge number of connections between the various topics, because it might be that you start with an alkane, you might then halogenate it, maybe then you do another reaction that substitutes the halogen for something else, and so on and so on. There are a lot of different ways that you can connect different functional groups, and they call this organic synthesis, basically. The idea of this is It has to do with kind of learning about chemical engineering processes and, you know, flow charts for making certain molecules or pharmaceutical synthesis. In other words, making drugs. Okay. Now, this is a little introduction to it because there's really only 3 conversions rather than, you know, quite a few, but it's a good time to kind of get up and running with it, but it is tricky. So what we have to do is break it down into some manageable chunks, right? What I'm going to suggest you do is copy the flow chart, including with the arrows labeled A, B, and C. Those are my labels, but just to point out process A, process B, and process C. For each of those conversions, have a go at naming the reagents, right? Have a go at naming every molecule that's involved in them, right? So the thing on the left, the thing in the top right, and the thing in the bottom right. Then, once you've kind of got up and running with it, see if you can name and outline the mechanism for each of those reactions, right? And also see if you can state the conditions for each of those reactions. So there is a lot going on here, and there's a very good chance that you won't do all this, but you can have a go, right? This is the kind of thing that if you're wanting to push yourself and really connect your knowledge, you know, you'll get something out of this, okay? And obviously I'm going to go through it step by step, but I'd like you to pause the video and see what you can make of it. Okay, so if you couldn't get very far, I'll just kind of remind you, feel free to have a look at your notes. All right, I've just spotted an error though, and you might have seen this yourself if you've been having a good go at it. All right, so that should not be there. All right, we're at the end of the video now, so I'm not going to re-record that. That's just my fault. I've copied something incorrectly. Either that or the error was in the exam question, but I think it's probably my fault. I had an extra hydrogen where I shouldn't have done. Okay, so if that was baffling you a little bit, I've just got rid of it. Okay, apologies for that, but it does happen. So then let's start to have a look at it together anyway. Okay, so conversion A, right? I've got the luxury of being able to copy and paste here, so I'm going to. All right. So just rejig that a little bit. This is really a question of playing spot the difference, essentially, right? What's happened when we've gone from the left-hand side to the right-hand side? And hopefully what you can see is that a chlorine atom has been added at this carbon, right? And a hydrogen atom has been added at this carbon. We've gone from CH2 to CH3, right? So what we've done is actually an addition reaction. We've added some stuff across the double bond because the double bond is also another difference, right? That was double, now it's single. So this links to what we've just been doing, right? This is actually completely related to the electrophilic addition to alkenes, okay? And the first thing that I really want to do is name the reagent. So if we think about it this way, we've added an H on that side, we've added a Cl on that side. There would have been a bond between those things. The reagent is hydrogen chloride. Okay, so that's what we have. So that was our first thing, reagent. Second thing was just to look at the organic molecules themselves. So if you had a go at naming these, let's have a look. So we're going to have here 3,3 dimethyl but 1-ene. I've had my confidence shaken now, so I'm just going to double check that that's the correct. We've got 4 carbon atoms in a row, but. We've got a double bond attached to carbon 1, and there's 2 methyl groups in the 3 positions. So yeah, I'm happy with that. Okay. Then in the next case, we've got rid of the double bond. So let's have a think about this, right? In this case, the numbering might well change. So it's going to end butane. all right, because we now no longer have a double bond, but we've still got 4 carbons in a row. We've got dimethyl again, but we've now got chloro as well. Now, we've got an option here. Do we have it as 2-chloro, 3,3-dimethyl, or do we have it as 3-chloro, 2,2-dimethyl? And the answer is we want the kind of combination that gives us the lowest numbers. So this is going to be 3-chloro, 2,2 dimethyl butane. And that's weird, but it has to do with the fact that we got rid of the double bond, basically, right, which had to take the 1 position. Okay. And therefore that made the methyl groups be in position 3. But now that that's gone, that kind of, that kind of set of numbers can be altered slightly. Right then, how about the mech? So we said it was HCl that we were going to add. We can probably use this version on the left, even though we're going to get rid of this version on the right for now. Okay. We've got a delta plus and a delta minus, curly arrow here, curly arrow there. Okay. Then we're going to have a carbocation intermediate. Okay, the hydrogen has been added to the right-hand carbon, so that's now a CH3, and we're going to have a chloride ion hanging around, ready to form a bond with this carbon. Okay. Now, there is actually obviously a major and a minor product in this reaction, but that's not what the question's about. Hopefully, if you're sort of, again, doing that kind of joined up thinking, you might realize that this is a secondary carbocation. So the thing that we looked at on the other side that we just named, right, that is your major product, right? Okay. And I'm not going to draw the formula of the product again because we've already done it, but there's your mechanism, and it is called electrophilic addition, which we've just been looking at in quite a lot of depth. So there's your name and outline. I think we've covered everything that was in that box. Reagent was hydrogen chloride. We named the organic molecules, named and outlined the mechanism. Conditions, there isn't anything. It's just hydrogen chloride, right? So this time you didn't need anything for the conditions, okay? That is going to be relevant in the other ones. So then, for B, have I still got this on my clipboard? Yes, I do. Lovely stuff. Okay. Now, let's pop it up there, actually. This time, it's the same couple of molecules, so we don't need to rename those. We've already done that, right? You can wind back in the video if you want to just check what they were, okay? But what we want to know is, how can we reverse that change? How can we make the conversion go backwards, basically? How can we turn the halogenoalkane into an alkene, right? And again, this is something that you might struggle with. If you're wondering when this was covered, it was in the halogenoalkanes topic. So it's not actually from the alkenes topic, even though it's a reaction that produces an alkene. And so there's absolutely no reason why we can't look at it in the context of alkenes. Okay. So, right, the reagent this time is going to be, and if you are looking it up and you want to find it yourself, then pause the video. But what we're going to be using is a hydroxide, specifically sodium hydroxide or potassium hydroxide. We might as well discuss the conditions now, though, because remember that when you react sodium or potassium hydroxide with a halogenoalkane, right, the nature of the solvent and the temperature actually influence what happens. So if it was cold and aqueous, then that would not perform this conversion. You would get an alcohol instead because you'd get nucleophilic substitution. Okay? In order to make this change happen, we need to raise the temperature and we need to use a large proportion of ethanol as our solvent. We say we use hot ethanolic potassium hydroxide to make this happen. So that doesn't cause nucleophilic substitution. Instead, this condition favors a reaction, or a mechanism type, sorry, called elimination. And it might have been hard to spot that, especially since it goes in reverse. I talked about that in one of the earlier questions, how sometimes reversing stuff makes it look trickier than it actually is. So let's tidy this up a little bit, get rid of that, okay, because what we want to do is think about the mechanism. Here's our halogenoalkane. And remember, what we're doing now is turning that back into the alkene that we had originally, right? In order to kind of help with this, we're probably going to want to draw out the carbon-hydrogen bonds. Okay? Because one of those hydrogens is going to need to go. Right then. So, right, the elimination mechanism which is favored when you use a high temperature and an ethanolic solvent, still involves the hydroxide ion, okay? And so what I'm going to do is I'm going to give you that for now, right? And see if you can figure out how the mechanism proceeds, or remember how the mechanism proceeds. So have a quick go at it if you've been struggling to get going and now you think you might be able to make a sensible suggestion. Otherwise, just wait. Okay, so remember that in the elimination mechanism, the hydroxide ion does not act as a nucleophile in the way that we, view it acting as a nucleophile like it does when it substitutes. Instead, we say it acts as a base. And a base in A-level chemistry is a proton acceptor. So what this hydroxide ion is going to do, I suppose technically, should specify that it's an ethanol, is it's going to take away a hydrogen ion. It's going to take away a proton, okay? Now, that's the first electron pair movement. And what that does is it forms a water molecule, okay? That hydrogen is being taken away and it's leaving its electron in that bonding pair. But the bonding pair isn't just going to dangle hanging down from the carbon. The bonding pair between the C and the H actually moves and is used to form the double bond between these two carbon atoms. Because remember, we're making an alkene, right? So there has to be a double bond between the two carbon atoms. At the same time, we can't now have that chlorine attached to that carbon. That needs to be booted out. So the chlorine acts as a leaving group and is eliminated. And that happens by moving the pair of electrons onto the chlorine, and the chlorine leaves as a negative ion. So you can do all that in one go. What you will get is the alkene that we had to begin with, missing a hydrogen atom and missing a chlorine, but we should point out that you'll also get the following byproducts, okay? A chloride ion and a water molecule. All right? So hopefully you're happy with that. Again, sorry for that initial mistake earlier. I feel bad about that, but hopefully we've all kind of got over it now. Right then, last little bit. Conversion C. So we're still aware of what this molecule in the top right is because we've dealt with that twice now in two different contexts, but we haven't actually looked at the thing in the bottom right at all yet. Okay. Right then. So again, we're playing spot the difference, right? How's it different? We've still got single bonds everywhere, so we've got no alkenes involved this time, but the chlorine atom has been exchanged for an NH2 group, okay? So again, in terms of like figuring out like what kind of reaction this is, it's a substitution because you've swapped something, right? You haven't just added something across a double bond, so it's not an addition, right? You haven't kicked something out of the molecule, so it's not an elimination. It's a swap, it's a substitution. And we need to know what kind of substitution it is. I've realized now as well that this amine, right, the thing with the NH2 group, there's no way you would be expected to name that for A-level chemistry, right? We can have a stab if you want, right? I'm not even sure what the actual UPAC name of this thing would be. There's two ways we can view it, right? The first way is, do we give the amine priority for the, for the one position, okay? So what I'm getting at is, are we going to call it just going to draw it again. Are we going to call this two methyl 3,3-dimethyl propyl amine? That's one possible name. The logic behind this name is that we're taking 3 carbons in a row, propyl amine, and then treating all the methyl groups as if they are branches, right? So hence you get 2, sorry, no, it wouldn't be 2, would it? It would be 1 methyl 2, 2, because this would be carbon 1, all right? Looks a bit funky, that. Like I said, you wouldn't be expected to name this for A-level chemistry ever. I guess another possible name is that if we leave those 4 carbons in a row, we might call it something along the lines of 2 amino 3,3-dimethyl butane. Or I suppose if we're numbering in the opposite direction to give lower numbers, we might call it 3 amino 2,2-dimethyl butane. None of this really matters because you don't have to name it. I probably shouldn't have asked in that initial box for you to name everything. If you had a go, then fair play. But just to be clear, none of this would be required for A-level. And like I said, I'm not sure exactly what name it is. I can look it up later on. I probably won't, in all honesty. Okay? Because you wouldn't be expected to do something of this complexity for A-level chemistry. Let's tidy up a bit and look at the mech. Okay. So if we just get rid of this arrow and get rid of the products, this is a nucleophilic substitution, right? That's the name of the mechanism. And the main thing is to spot what our nucleophile is. So we're going to get nucleophilic substitution, and our nucleophile has to produce an amine. So you should hopefully remember that our nucleophile is going to be ammonia. Okay? So usually when we're doing this type of mechanism, we just draw the ammonia as NH3 and put a lone pair on it. Okay? You're going to have a partially positive carbon and a partially negative chlorine, and we're going to have 2 curly arrows initially. Nucleophilic attack on the carbon by the ammonia, and movement of the bonding pair between the carbon and chlorine onto the chlorine. Okay, so that's your first 2 steps. Then it's not just as simple as doing the product, because something else has to happen in order to make that amine that we had. Just check that I'm copying the structure correctly. When the ammonia attaches, remember that it has a positive charge initially. So let's say we've booted out our chloride ion, okay? There's now a positive charge on that, right? And in the product we had, you didn't have NH3 plus, you had NH2. Now there are kind of problems with this, but don't worry about it. Let's do what the kind of exam question wanted, which is think about how we'd have made it into NH2. The thing that we learned was that one of the conditions for this reaction would be that there's an excess of ammonia. So that's part of the conditions. Your reagent is ammonia and it is in excess. That's a condition. Sometimes you also see it referenced to being under pressure as well, but I've not really seen that needed in an AQA exam question. We then have another couple of curly arrows. The second ammonia molecule acts as a base, a proton acceptor, takes away a hydrogen ion from that positively charged part of the structure, and the pair of electrons that was holding that hydrogen in place moves on to the N and basically gets rid of that negative charge. Okay? So then the final structure, well, we've already got it. We already drew it. It was with an NH2 on the end of the carbon. Right, so that last bit, definitely a bit challenging, right? Tripped me up a couple of times with silly things like drawing carbon with 5 bonds, but that just goes to show if you don't take, proper care and attention, then you will make daft mistakes, and it happens to us all. But the main thing is that hopefully we've got something out of it. If that last bit just seemed like way too hard for you, don't worry too much, because the synthetic roadmap stuff is really something you do towards the end of the A level, right? It's just that there's no harm introducing the idea at this stage. And if you can't remember, like with the mass spec, if you can't remember anything about halogenoalkanes, my recommendation is that you go back and have a look at your notes on halogenoalkanes, because it'll help. All right, thank you for listening.